Hello. We're going over a AP practice problem using the concept of equilibrium, but it's a gas problem where you have to use Kp and you have to use some of the specific properties of the partial pressures of gases and the total pressure of a mixture of gases to get this problem right. So, special case of equilibrium. So in general, the rules are going to be the same. We're just paying attention to gases. Okay, so here is our reaction. We have ammonium hydrogen sulfide. It is a solid. Solids don't participate. Make sure that you keep track of that. Don't participate in an equilibrium expression. Makes ammonia and makes hydrogen sulfide. So that's my outlook. Our approach is going to be roughly the same as before. So we're going to use 4 different categories of work. I'm going to have a rice table to organize information. We're going to need Q, and we're going to need to write out the equilibrium expression. We are going to plug in the equilibrium expression, perhaps, to find K. We're going to plug in the equilibrium conditions from the rice to find K if we need to find K, or we're going to use any information we have about those equilibrium conditions, including the total pressure, to solve for K if that's what we're looking for. And we're going to make sure that we are answering the question asked by the problem, because there are many things to answer along the way. Okay, so again, these are the 4 different areas that you have to keep track of. Rice, Q, K, and then your work, your math work. So let's get started with part A. So we already talked about the reaction. So it's a solid that's slowly decomposing into 2 different gases. Ammonium hydrogen sulfide is placed in an evacuated vessel. It means there's nothing in it. It tells you something about the initial conditions. After equilibrium is attained, the total pressure is found to be 0.659 atmospheres. Some solid remains in the vessel at equilibrium. Why is this important? We know that we have reached equilibrium and there are still more ammonium sulfide particles left. So it's not a excess limit. Nothing is limiting. It's going to reach equilibrium as it would without having to worry about how much solid there is. So with that sentence telling us that there's some solid left in the vessel, we know we don't have to worry about it. We're not going to run out of it. We have more than we need. For this decomposition, write the expression for Kp and calculate its numerical value at 25 degrees Celsius. Beautiful. So there will be lots of calculating. We have to know how many sig figs we're going to use. How many sig figs do we have? Look around. So here's a number, atmosphere. So total pressure inside of the vessel. Here's another number, 25 degrees Celsius. However, hopefully you have been taught never to write down the temperature in Celsius. Always convert it to Kelvin before you do that. So the chemistry gods know that you are going to convert that to 298 Kelvin. So 25 degrees Celsius is 298 written in code. So you look at it, you only see 2 significant figures, but in reality, we all know it's 298. And it's not 299, 297, it's 298, because the 273 isn't a precision thing. It's not, it doesn't have to do with how carefully something is measured or with the type of measurement instrumentation. It's the way you get from Celsius to Kelvin, but it's really 273.15, I think, but we're going to ignore that. It's 3 sig figs. Okay, write the expression for Kp. Excellent. I know how to do that. Equilibrium expressions. K equals brackets, products, brackets, reactants. Yay! Sometimes there's coefficients. Right? Like NH3. They all have coefficients of 1, so they're raised to the first power. No. That is for concentration. That would be Kc. I want Kp. Kp is written differently. It is partial pressures. So square brackets mean molarity. It is, in fact, partial pressure of NH3 times the partial pressure of H2S over 1. So we mentioned that at the beginning, oh, look, it's a solid. Make sure you don't put it into Kp. It does not go into the K. So when there is a solid or a pure liquid, we ignore it completely in the equilibrium expression. Don't let it throw you off. You're not doing division by 0 or anything like that. You're just saying 1. It does not influence. So an easier way of writing Kp is to just say it's the partial pressure of ammonia times the partial pressure of hydrogen sulfide. Okay? That is the Kp. That was the first thing I was asked to do. Okay, so we've written the expression for Kp. Now we need to calculate its numerical value. So, what do? Let me start constructing my Rice table. So, let me write out my reaction. I'm going to use whatever information I was given. So, I was told that there was some solid that was placed in an evacuated vessel. Do I care how much solid there was? Nope, solids don't come into it. It was evacuated, therefore I know exactly what the partial pressures for NH3 and H2S were. They were 0. So this is my initial condition. Nothing to do with the solid. You don't have to write anything there if you want. I like writing lines just so I know that I don't know, empty space bothers me sometimes. Okay, so we want the numerical value. So we want the partial pressures of both of these guys. We have to get this number and multiply it by that number to find Kp. So we're building our way to those values. The next step is the C, the change. What is the direction of the change going to be? Well, I can't have less than 0. I can't move to the left and make more solid. Therefore, I'm going to have to move to the right. I can only increase. So Q equals the partial pressures multiplied times each other. Same expression as for K, except I can plug in the partial pressures at any time. So Q initially is 0. 0 times 0. If Q is 0, it means that the entire reaction is going to move to the right, towards the products. So it is going to be positive on the side of the products. Yes, there's going to be a loss of ammonium hydrogen sulfide. So I could write minus X, but think about what X represents. X represents a pressure, a partial pressure. So it really only makes sense if I'm dealing with a gas. NH4HS is a solid. It doesn't really have a pressure. I mean, it's got some vapor pressure, but it's tiny. It really doesn't make sense to write negative X there. So I'm just going to ignore it. Okay, so I now have a way to write the equilibrium expressions, right? The equilibrium expressions are X and X. Woohoo! Okay, not that exciting. So, what do I do next? Well, let me see what other information I have. So, after equilibrium is attained, the total pressure inside the vessel is found to be 0.659 atmospheres. blah, blah solid. I don't care about the solid. So at equilibrium, that means follow the line that starts with the E. So at equilibrium, there's NH4HS. I don't care. There's X partial pressure of NH3, and there's X partial pressure of H2S. Can there be other gases there? No, it was evacuated. There was a vacuum. It was empty before we started. So the only possible gases there are these two. There are equal amounts of them. Together, they add up to a total pressure of 0.659 atmospheres. I can use that fact to solve for X. Once I've got X, I can find Kp. So, when we're dealing with gases and you have a total pressure, what you have is the sum of all of the partial pressures. So in this case, there are only two gases. So the sum of those two partial pressures must add up to 0.0659. Yeah. So I haven't said anything new. I've just pointed out that the total pressure has to equal the sum of those two things, because those are the only two things that are available. Okay. What's the partial pressure of NH3? Why, at equilibrium, the partial pressure of NH3 equals X. What's the partial pressure of H2S? Why, at equilibrium, it also equals X. So now I have algebra that I can deal with. So X plus X equals 0.659. I wonder how big X is. Pause. Solve it yourself. So, it looks like I did this out of order. Yes, I did. Okay. So I would rewrite that as 2x equals 0.659, and then I would divide by x, and I get 2 3 sig figs. Remember, 0.330 atm. That is the partial pressure. Yes, that is the partial pressure of each of those gases at equilibrium. Now, the general rule, what I need you to take away from this is the slide that I just tried to skip. Okay, that in general, when you have gases, so this is a generic reaction gases A, B, and C. So let's say that at equilibrium, I have all three gases. And I just assumed that I started out with 0. These details aren't important, they can change. The important part here is that if you're given the total pressure, what you have is the sum of all of the partial pressures of the gases. So that usually serves as the equation that lets you solve for everything. So here we don't have X and we don't have K. In other examples, I've given you either a way to find X or a way to find K, and we use one to find the other. Here, I don't have to give you either, I just give you the total. And I need you to apply this extra knowledge that you have, that the total is the sum of everybody at equilibrium. So thinking of this little loop at equilibrium, that all of these guys add up to the total, is a very robust way to solve gas problems. Okay, that is the general rule. Okay, so I've got X, and I have written, that X equals 0.330 underneath those, just to keep all of my information on my rice table. Okay, am I done yet? I was asked for Kp, the expression for Kp. Yep, it was partial pressure of NH3 times partial pressure of H2S, and to calculate its numerical value. No, I found X. I didn't find Kp. Almost there. Okay, so the equilibrium expression is the same thing it was a couple slides ago. NH3 times partial pressure of NH3 times the partial pressure of H2S. Okay, so in this case, there I am. in this case. They both equal the same number. What number do they equal? 0.330. So Kp is just 0.330 squared. Kp equals 0.109. No units. So we're officially done with part A. Take a breather. Let's look at part B. Okay, so extra gas is injected into NH3 gas, is injected into the vessel containing the sample described in part A. So everything that we dealt with is there. Equilibrium is re-established at 25 degrees Celsius. The partial pressure of NH3 in the vessel is twice the partial pressure of H2S. Okay, so we had equilibrium. We had 0.33 ATMs of each. Someone came by and injected. I just noticed that 2 should be a 3. I'm sorry. That's a 3. Someone injected some extra NH3, which is a stress on the equilibrium is going to cause a shift. What do we know about the new equilibrium conditions? We know that at the end, the partial pressure of NH3 is twice the partial pressure of H2S. Calculate the numerical value of the partial pressure of NH3 and the partial pressure of H2S. Got it. After equilibrium has been reestablished. So I have a whole new rice situation. My initial conditions are no longer the 0. My initial conditions are the previous equilibrium with somebody coming by and stressing it by adding some NH3. So let me see what this information looks like. I've got my initial conditions. I still don't care about the solid. I'm sorry, solid. And I still don't know how to move this. It's driving me insane. Okay. So I had 0.33 and some of that was added. So I've had an increase. I had my reactants and products were in perfect balance. I've had an increase of my products. That means that there is going to be a shift. In what direction? It's going to go to the left to reduce the NH3 and increase the solid. So think about it. That would look pretty weird. You add a gas to a system that has stopped changing and it starts to create a solid at the bottom. So I don't know how much has been added. I know the direction of the shift. I know that it's going to go to the left, therefore there's going to be less than 0.33 of the H2S. But I don't really know how much was added. And that whole adding the plus X on the side of the solid still makes me uncomfortable because these numbers are partial pressures. So I'm not super happy with this setup, but at least I know what's happening. I can picture what's happening. Okay, so what else do I know? I know that the partial pressure of NH3 is twice the partial pressure of H2S. So how can I write that? Partial pressure of NH3 equals 2 times the partial pressure of H2S. I just wrote it down. Okay, so what else do I know about the relationships between the two? Well, I know that at equilibrium, the Kp is always equal to the same value, the 0.109, I think it was, that we got a little while ago. And that's a relationship between these two variables. If I have two equations, two unknowns, with a system of equations that is solvable. So I am going to combine the information that I just got about the equilibrium conditions with what I know about Kp. So I know that when these two variables are multiplied together, I will always get 0.109. I also know that one of the variables is twice the other. If this looks weird, just call them x and y. You have x times y equals 0.09, and you have that x equals 2y. System of equations, go for it, solve it. Pause this, come back to me when you have x and y. I'm going to continue with this notation though. So I'm plugging in, instead of NH3, I'm plugging in 2 times PH2S. Yeah, substitution. It's all good. So 2 times my variable equals 0.109. Therefore, 2 times the variable squared equals 0.109. What do? I divide by 2. I take the square root of everybody. I try to get rid of this, and it doesn't really help. Okay, so again, unless I've done a math mistake, this is my answer for the partial pressure of hydrogen sulfide. So I divide by 2, I got the 0.0545, then took the square root, and I end up with a partial pressure of 0.233, which is less than it was in the beginning. In the beginning, it was 0.330. And we had said that it had shifted in the opposite direction. So I should have a number that is less than 0.33. Yes, I have a number that's less than 0.33. Yay. Okay, so do I have the final answer? Am I done yet? So I calculated the numerical value of, not both of them. I've calculated for H2S. I still need to find it for NH3, but I know that for NH3, it's just twice the partial pressure for H2S. So all I have to do is a tiny bit of math, and I have my answer. Do your own math. Check. So I just multiply, and I end up with a partial pressure of 0.466. So these two are my answers. They are pressures, therefore they have units. K doesn't really have a unit. That unit is not very informative, but pressure does have a unit. And we're done. Yay! Next, part C. Okay. I still need to fix that. That's a 3. Okay. So in a different experiment, both of the gases are introduced into an empty 1 liter vessel at 25 degrees Celsius. So nobody mentioned that there was any of the solid, therefore there was no solid. That isn't even you making an inference, that's assume that to be true. The initial partial pressure of each gas is 0.5. I'm ignoring the other sig figures because I already said all these problems have 3 sig figs. So I just have to think, and I just have to check my answers. Okay, so calculate the number of moles of the solid ammonium hydrogen sulfide that is present when equilibrium is established. So I have a new Rice situation, new initial conditions, new change, new everything. Do I have a new KP? No. I'm at 25 degrees Celsius, therefore the KP still equals the value that we found in the previous part, the 0.109, I believe. So I know the relationship between, I know that when I multiply the two gases, the partial pressures of the two gases, I'm going to end up with 0.109. That's the equation that's in my pocket. And I know how to set up my information in a way that will be useful. So set up your Rice table. Write down your initial conditions. And meet me in the next slide. Okay, so 0.5 and 0.5. That's it. Okay, so before we were starting with 0, so we started with Q equals 0, so we knew that we had to produce something because we needed a value. There's no such thing as a less than 0 pressure. So now we don't have a 0. We actually have to find Q and figure out whether Q is greater than K or not. So Kp, we know, equals 0.109. We need to find Q and see whether it's less than that or more than that. And that will tell us the direction that we're going to take. Okay, so solving for Q. Q equals the partial pressure of NH3 times the partial pressure of H2S. Check. Okay. Therefore, you are going to substitute those values, and we're going to see what that equals. And we're going to figure out whether that number is greater than or less than 0.109. So take a calculator, find me a value. So Q equals 0.25. Now, I know Q, I know K. What information can I get from there? Well, last time I checked, 0.25 was larger than 0.109. That means that the reaction has too much product. It's going to flow towards the left to reduce the amount of product, to reduce the amount of gas. Okay, so my goal was to predict the direction of the change. I now have the direction of the change. So I can go back to my rice table and I can write the C part. So, it is now, negative X on the side of the products, positive X. Again, that X doesn't really have any meaning. I don't have to write it there because it's a solid, but it's a habit. Okay, so at equilibrium, how much NH3 do I have? Well, I have 0.5 minus X. At equilibrium, how much H2S do I have? 0.5 minus X. Okay, so here's an unknown. I need to get numbers for these values. So what else can I use? So I have a rice table. I used Q. Let me go to K. That's the next thing, like in space. Let me see if K is useful. So the K expression is that when you multiply these two values, you end up with 0.109. So if I multiply these two values together, I should end up with 0.109. Yeah, because that's what the partial pressure of NH3 at equilibrium is, 0.5 minus X. I'll multiply it times the partial pressure of hydrogen sulfide. Oh, look, that's 0.5 minus X as well. So I end up with this expression, 0.5 minus X times 0.5 minus X equals 0.109. One equation, one unknown, solvable. You can FOIL and do the thing and have an X squared and use the quadratic equation. However, the AP seldom to never makes you do that. There's usually an easier way. So you find yourself in a situation where something is multiplied by itself. I need your brain to say, ooh, that's a square. You know what a square is? I need your brain to say, ooh, I can write that as 0.5 minus X squared before you go to the ooh FOIL. Because I know like your math brain has probably been trained that way. I need the chemistry part to be a little louder and say, no, don't do it. Just write it as a squared. Okay, so I can take the square root of both of those sides of the equation, right? So in the math world, that's not cool because you're eliminating the negative solution. You're eliminating one of the roots, and those are actual things. For us, I'm eliminating an imaginary solution. There is no such thing as a negative partial pressure. So I can do that in Chem. So I'm going to solve this. I'm going to take the square root of both sides. I'm going to solve for X. Pause me and solve it for yourself. So the square root was 0.33. I knew that. Didn't we use that number before? 0.5 minus X equals that. I'm gonna, here, I always do two steps at once. Sorry if that's confusing. I add X to both sides, and then I subtract 0.33 to both sides. Anyway, you take your algebra root. Hopefully we'll end up with 0.170. I'm keeping the 3 sig figs. I lost them there temporarily. Okay, are we done yet? Am I done yet? Is this my final answer? Well, what did the question ask for? The question asked me to calculate the number of moles of solid NH4HS that is present when equilibrium is established. So, no, I'm not done. What I have is X, which was the change in partial pressures for both of the gases. Yeah, so I'll take you back to the Rice table so you believe me. That's where the X came from. So this X is the pressure that was lost in both cases. Okay, they have an equal pressure. So that was not my final answer. How am I going to approach this? Well, X is the change in partial pressures for NH3. Why did the partial pressure reduce? Because some of the moles of gas were reduced. Nothing else is changing. The temperature isn't changing. The volume isn't changing. It must be the number of moles. So the moles of gas reduced. If I can find out by how many moles of gas it was reduced, how many moles of gas were lost, I'll be able to use the balanced reaction, stoichiometry, to find how many moles of the solid were produced. And that's actually what I'm looking for. So, time for the ideal gas law to get from this loss of partial pressure. How many moles have to be consumed to account for this loss of 0.17? So, ideal gas law. Solve for the moles of either of these gases. Doesn't matter which. Pause me, work on that, and then look at my answer. Okay, so this is my reaction. I'm going to pretend that I'm dealing with NH3. It really doesn't matter. Avogadro told us that any gas under the same conditions occupied the same volume. So I can say that it can be either one of those gases. If it makes you happy to think about a specific one, let's call it NH3. So this is the ideal gas law. PV equals nRT. I'm solving for n, so I'm going to regroup for n equals PV over RT. I have all of those numbers, so I'm just going to plug them in. N equals, P is 0.17. That was the partial pressure that was lost. The volume was 1 liter. It said so in the problem. R is the ideal gas constant. If you want to use the 0.08206, be my guest, but your numbers will be a little bit off from mine. And the temperature is 298 K, not 25 degrees Celsius. Please don't make that mistake this far in. Okay, so unless I've made a mistake with my math, you end up with a very small amount of moles, and that's okay. So this many moles, 0.00694 moles of NH3, to pick a gas, have been consumed. Do you know how to do the stoichiometry of going from moles? If this many moles of NH3 were used, how many moles of NH4HS were produced? Yes, you can totally do that. So it's just a 1-to-1 ratio, but I'm going to write it out. So because for every 1 mole of NH3, there's 1 mole of NH4HS. It is a 1-to-1 ratio. Therefore, how many moles of the solid are produced, which is the question that I'm being asked. Exactly 0.0694 moles of NH4HS are produced. And yes, that is the final answer. So that took a while. Let us look at the path we traveled. Here is the problem. No, here is the problem. Okay, so part A, Those were the good old days. We were asked to write the expression for Kp. All good. The only weird thing was we had to remember that the solid did not participate. It was just treated as a 1. Calculate its numerical value. We used the fact, and this is an important generalization, we used the fact that we had the total pressure. The total pressure equaled the sum of all of the gases. So with that little piece of information, we were able to unlock what the X was, and then we were able to find Kp. Okay, so part B, we have this, we had equilibrium, it's been stressed, it has shifted, we figured out the direction of the shift, but ultimately what we had to do to calculate the numerical value of the partial pressure was to use this relationship, that at equilibrium, the amount of NH3 was twice the partial pressure of H2S. That became one equation. The other equation was the equation for Kp. I had 2 equations, 2 unknowns, and I was able to solve. Okay, part C. I had a new situation, starting out with gases instead of starting out with 0 gases, making the solid. So I did the same rice thing. I checked to see what Q was, to see what direction it was going to move in. Don't just assume that you're making products. Sometimes you're using up products. That plus the equation for Kp led us to figuring out how much the pressure had changed. Given that, we used the ideal gas law to find how many moles had been used, and then stoic to find how many moles of the solid were produced. So, hopefully that made sense. Please practice these problems.